Dear students, so far our discussion was based on how to test the significance of one population mean and also how to construct confidence intervals for one population mean. When population standard deviation is known and also when the population standard deviation is unknown. But there are many situations in which we may have to compare two or more populations. Two or more populations. For example, we may have to compare whether the mean age of new domestic cars whether the mean age of buyers of new domestic cars is greater than the mean age of buyers of imported cars. Or we may want to determine whether the average marks received by male students is different from that of female students. Whether the income received by one group of persons is different from another group, etc., etc. So we have to consider situations in which we have to compare the mean values of two or more populations. Now we consider two types of inferential procedures for comparing means of two populations. For comparing means of more than two populations, we require what is known as ANOVA procedure that we will discuss later. Now we consider how to compare the mean values of two populations. We consider two cases. One is when the samples from the populations are independent. That is, samples taken from two populations are independent. The second case is samples from the populations are paired, such as husband and wife, such as two types of fuel on the same car. So we consider the cases in which samples are independently taken and also paired samples. Now in this session we consider how to compare mean values of two populations independently sampled. The first step in the comparison of mean values of two populations is derivation of what is known as the sampling distribution of the difference between two sample means. So we first consider how to derive the sampling distribution of the difference between two sample means for independent samples. Remember this, for any hypothesis testing, We assume that we have a sampling distribution. To test the significance of one population mean, it was assumed that the sampling distribution is that of x bar. X bar is a random variable and it is normally distributed, assuming that the population from which sample is taken is normally distributed. So here we consider the sampling distribution of the difference between two means, difference between two sample means for independent samples. And the method which we discuss require that the samples are selected from two populations with a simple random sampling and also independent samples. Simple random sampling technique is used to select samples independently from both the populations. For example, if you want to compare the marks of the students from boys and girls are independent, and we assume that we select samples using simple random sampling procedure. To explain how we compare the two population means, we consider an example. The example is the American Association of University Professors conducts salary studies of college professors, and suppose we want to decide whether the mean salaries of college faculty in the public and private institutions are different. We want to compare the mean salary of college professors from public and private universities. The data is given in the book, and to formulate this problem statistically, we have one variable. The variable is salary from two populations. One is the entire public universities of USA. The other one is the entire private universities of USA. So we have one variable salary, and the other one is salary from two populations, public universities and private universities. So population 1 is all faculty in the private universities, and population 2 of faculty in the public universities. We assume population 1, population 2. And we denote the mean salaries of the faculty as mu1 and mu2. Mean salary of faculty in the private universities is mu1, and mean salary of all the faculties in the public universities mu2. And we formulate our null hypothesis as H0 mu1 is equal to mu2, or mu1 minus mu2 is equal to 0. Our null hypothesis is that there is no difference in the mean salary of faculty in the public and private universities, in the population, not in the sample. Mu1 is the mean salary of all faculty in the private universities. Mu2 is mean salary of all faculty in the public universities. Now, we can carry out the hypothesis test as follows. Let us see what are the steps. Once you formulate the hypothesis, so this is step 1. In the second step, what we do is we independently and randomly take samples from private and public universities. That is, we take samples, say N1 samples from private faculties, faculty in the private universities, N2 faculty in the public universities. And we calculate what is known as x bar 1. That is the sample mean salary of the samples selected from faculty of private universities, and x bar 2. That is the sample mean salary of the faculty from public universities. And the data is given in the book. And let us assume that x bar 1 is 19 and x bar 2 is 83.18. This is the sample mean salary of faculty in the private universities. This is the sample mean salary of faculty in the public universities. Now, as you can see, there is a difference of 15.01 in the salary between faculties of private and public universities. Now the question is this difference due to sampling error, or is this difference is due to the fact that there is a difference in the mean salary in the population? Is this difference due to sampling error, or is this difference due to the fact that there is a difference in the mean salary in the faculties of public and private universities? Now, to answer this question, we have to define what is known as the distribution of the difference between sample means. To answer this question, we must know the distribution of the difference between the sample means, known as the sampling distribution of difference between sample means. Sampling distribution of difference between sample means. Sampling distribution of the difference between sample means. To answer whether this sample means observed is due to sampling error or due to differences in the mean values in the population, we have to define, or we have to derive the sampling distribution of the difference between sample means. So, to make inferences about the difference between means, the first step is we have to formulate H0 and H1. H0 is mu1 is equal to mu2, or mu1 minus mu2 is equal to 0. And H1 can be mu1 not equal to mu2, mu1 greater than mu2, or mu1 less than mu2. H1. So H1 can be mu1 not equal to mu2, mu1 greater than mu2, or mu1 less than mu2. This is a two-tailed test. This is a right-tailed test, and this is a left-tailed test. Terminologies we have studied earlier. So the first step is we formulate the hypothesis, the null hypothesis, alternative hypothesis, and whether the test is two-tailed, right-tailed, or left-tailed depends on how we formulate the alternative hypothesis. Now, we can also compare two population means with the confidence intervals. As we have considered the construction of confidence intervals earlier, and depending on alpha, we know 95%, 90%, 99%, etc. confidence intervals, and the interpretation is also familiar to us. But in the case of comparing two means, the interpretation of confidence intervals is different. Let us see what it is. Let us see how we actually interpret confidence intervals when we have to compare two population means. One, if the endpoints of confidence intervals are positive numbers. So for example, suppose that 95% confidence interval for mu1 minus mu2 is 3 to 5. 95% confidence interval for mu1 minus mu2 is 3 to 5. It means that the interpretation is we can be 95% confident that mu1 minus mu2 lie between 3 and 5, or we are 95% confident that mu is somewhere, mu1 is somewhere between 3 and 5 greater than mu2. If confidence interval for mu1 to mu2 positive numbers, then 95% confidence interval for mu1 minus mu2 is mu1 is 3 and 5, mu1 is somewhere between 3 and 5 greater than mu2. Now, if both negative numbers, then it means that mu1 is 3 and 5 less than mu2. Somewhere between, mu1 is somewhere between 3 and 5 less than mu2. If confidence interval is, say, one is positive, the other one is negative, minus 3, 5, then the interpretation is mu1 is 3 less than and 5 more than, somewhere between, mu1 is somewhere between 3 less than and 5 more than mu2. So remember these interpretations. If the end points of confidence intervals are positive, then it means, suppose that the end points are 3 to 5, then it means mu1 is somewhere between 3 and 5 greater than mu2. Negative, mu1 is somewhere between 3 and 5 less than mu2. Minus 3 and 5, mu1 is somewhere between less than 3 and greater than 5. This interpretation should be kept in mind when you construct confidence intervals for difference between two means. Now we consider the sampling distribution of the difference between two sample means for independent samples. Now we consider a few notations. Now suppose that this is population 1, population 2. Given that we have two populations, 1 and 2, population mean mu1, mu2. Population standard deviation sigma 1, sigma 2. Sample mean x bar 1, x bar 2. sample standard deviation sigma of x bar 1, sigma of x bar 2, sigma of x bar 1 or sigma of x, sorry, no need for writing sigma, x bar 1, x bar 2, S1, S2, because S1 is the standard sample standard deviation, sigma 1 is population standard deviation, S1 and S2. Then sample size N1 and N2. These are the notations which we use. Population mean mu1, mu2, population standard deviation sigma 1, sigma 2, sample mean x bar 1, x bar 2, sample standard deviations S1, S2, sample size N1 and N2. Now, given these notations, we derive the sampling distribution of difference between two sample means. Sampling distribution of the difference between two sample means. Suppose that x is a normally distributed variable on each of these two populations. Suppose that x is mark, the variable mark of male and female. And suppose also that the variable x mark is normally distributed on male population and female population. Then for independent samples of size N1 and N2, independent samples of size N1 and N2 from these populations, it can be shown that mu of x bar 1 minus x bar 2 is equal to mu1 minus mu2. Mu of x bar 1 minus x bar 2 is equal to mu1 minus mu2. Sigma of x bar 1 minus x bar 2 is equal to sigma of x bar 1 minus x bar 2 is equal to root of sigma 1 square by n1 plus sigma 2 square by n2. Sigma 1 square by n1 plus sigma 2 square by n2, and x bar 1 minus x bar 2 is normally distributed. And this is the sampling distribution of the difference between means x bar 1, x bar 2. What does that mean? We know that for a single population we have x bar and we have the distribution of x bar if we take repeated number of samples. Here also we take, and we also know that its mean is mu. Now here we take a repeated number of samples and note the difference between x bar 1 and x bar 2 each time. And this first line suggests that if you take the mean of this x bar 1 minus x bar 2, it will be equal to mu1 minus mu2, mu1 minus mu2. And what is here? X bar 1 is mu with the sigma by root n, the standard deviation. Here sigma of x bar 1 minus x bar 2 is root of sigma 1 square by n1 plus sigma 2 square by n2. And the random variable x bar 1 by minus x bar 1 minus x bar 2 is normally distributed. And this is the sampling distribution of the difference between two sample means. And this distribution is used for testing whether there is a difference between the mean values of two populations. And the standardized version of this quantity is Z. Z is equal to x bar 1 minus x bar 2 minus mu1 minus mu2 by root of sigma 1 square by n1 plus sigma 2 square by n2 z, the standardized version, and this is the test statistics used to test the difference between two population means, where z is the standardized version of the random variable x bar 1 minus x bar 2. Remember this? The distribution is x bar 1 minus x bar 2 with this is mu1 minus mu2, and its standardized version is z. So this random variable, that is x bar 1 minus x bar 2, and its sampling distribution is used for hypothesis testing. Now given this, once we specify the value of mu1 minus mu2, and when you test the difference between two means, the null hypothesis is always mu1 minus mu2 is equal to 0. Then z becomes x bar 1 minus x bar 2 by root of sigma 1 square by n1 plus sigma 2 square by n2, always, because it is minus 0. So this is the test statistics used for hypothesis testing. So the procedure is, you calculate the difference between x bar 1 and x bar 2, calculate the quantity, the variance or the standard deviation of x bar 1 minus x bar 2, you will get z. Compare z with the critical z values and take a decision. But remember this procedure requires that sigma 1 square and sigma 2 square are known. Sigma 1 square and sigma 2 square are known. But we know that this procedure will not work, because in most cases and in all cases these population quantities are unknown. So we will not develop this procedure further. We will replace this with the sample counterparts, and we have the t-test. So for comparing the difference between two means, or to compare two populations, what we generally use is the t-test procedure. But remember this is the procedure used for comparing two population means using z test, on the assumption that the population variances are known. So this procedure is known as two sample z test, or two sample interval procedure, or simply two sample z procedure. But remember also this procedure is not generally used in applied empirical research, due to the fact that these quantities are unknown. But from the theoretical perspective, this is the two sample z procedure for testing the difference between two population means.